Okay, so that's just about that. Again, interchanging just between mu and lambda, which are just two dummy indices, and we're not going to get any minus sign for doing that. Again, because we're not just interchanging between mu and lambda, that is just on this field tensor. Now, if we do that, this expression gives us finally f, this will be lambda mu, yes, and then this will be mu, beta, and our comma here, but then lambda here. Now, looking at this expression, of course, again, at this point in time, we may decide, so we've just made an interchange between these two, and then we have mu and lambda here. We may just decide, for instance, to perform an interchange between mu and lambda once again. And so this will give us, for instance, minus of f mu lambda, but then f mu beta, comma, lambda. And then if I interchange between the mu and beta here, I'm going to get that minus that I will obtain by interchanging between these two indices on this field tensor, cancels that, and what I have will be f mu lambda, f, but then beta mu, comma, lambda. Yeah. So in other words, this whole expression that we had here becomes 1 all over 2. And so you can note that I just combined these two factors and perform all these transformations and arrived at this. Now you can see that once again, this f mu lambda is still common, and of course which is common to all of them. So I'm simply going to write this again outside, f mu lambda, and then what I'm going to have inside for the first term becomes f beta mu, comma, lambda plus f lambda beta, comma, mu, and then again let me say plus here, f mu lambda, comma, beta. So you can see that I've been able to write this. So I have 2 times of this, and I wrote them as 1 of that plus 1 of that. So this is just again the same as that. And then the combination of 1 of this factor and 1 of this, either this 1 or that one, was what I did to change this f lambda beta mu to now f beta mu lambda, and which is what I have for my first term here. So if I were to be very redundant, all I'll do will be to open up this bracket, work on that very first term, and then I'll end up with this. Then once again I'll say, well, f mu lambda is common to all of them, and I'll pull it out again, and of course the half is common again, and then I'll pull it all out, and then I'll be left with this in the bracket. Looking at what we have here on the bracket, I can just look at this again. Remember, we have commas here and comma. Just between, after the first 2 indices, there is a comma. Maybe I should look at this from here. Yeah, exactly. So if I perform a cyclic permutation whereby I pull lambda to come here and take the place of beta, beta takes the place of mu, and then mu comes at the back, and this is what I get. If I take mu again, coming back, it takes the place of lambda, and then lambda takes the place of beta, and beta returns back to the last place. So you can see that the contravariant analog of the homogeneous part of the homogeneous Maxwell equation is simply equal to that, and you can agree with me that this is equal to 0. Well, if you don't agree with that, you can decide to lower all the indices on that with a lot of metric tensors, and maybe about 3 for each term. But then again, you will just arrive at that particular factor, or this term being equal to 0. So in other words, we have been able to show that these last 2 terms are equal to 0. And that being said, it means that we can see already, yeah, so there's no point, I think I'm done, or maybe I can just box it in. We can see already that if I were to multiply this out, what we have is that the alpha beta is equal to minus 1 over c, j sub lambda sub f lambda beta. So just like we guessed from the beginning, since there are sources here in this Lagrangian, in this case, and our Maxwell equation in this case is this equal to that and not 0, our energy momentum tensor isn't conserved, and this is what we are going to get. So this part, again, of course, you know, in the absence of sources, which means that J will be 0, again, this will have been 0. But now, in the presence of sources, it's not. And rather, when we contract alpha and mu, or we find some kind of 4 divergence, we obtain this to be equal to minus 1 over cj sub lambda f lambda beta. And so that's not about that for that one. Okay, very quickly again, we can just show that the same thing arises when we consider the Proctor Lagrangian. And the Proctor-Lagrangian, again, using the Euler-Lagrange equation, is a very simple exercise to show that when you substitute this Lagrangian in that equation, you obtain this as the Proctor's equation of motion. Almost the same with the Maxwell equation again, except for this term. And then again, in the gauge, in the Lorentz gauge, one other thing again is that this homogeneous part of this equation is applicable even for the Proctor fields or the Proctor-Lagrangian. So we have just two forms of that. We have this as one of the equations, and also again, just like I've written here, to avoid writing that multiple places. So we have the alpha f alpha beta to be equal to 0, just as we had it here. So you can say that the complete Proctor equation of motions is a combination of this and that. This again, just as it was for the Maxwell equations, we had this one here and this one. For the Proctor fields, again, is this one and that. And so, having said that, we are saying again that in the Lorentz gauge, this equation obviously reduces to that. And then again, of course, in the Lorentz gauge, you know that if I were to differentiate this expression with respect to alpha, that is, by performing this calculation, I'll end up getting 0 still because, first of all, you know that in the end, this partial differentiation here, how will I put it, commutes with the D'Alembert. And if it commutes with the D'Alembert, it means in the end, I'm going to do something like this, A alpha here. And for this time again, I'm going to get another, the alpha A alpha. And since we're assuming the Lorentz gauge, which implies this equal to 0, and that implies that that is also equal to 0. So the current density again, in this case, is still conserved for the Lorentz gauge. So we just have to keep that in mind. Now we want to show, and that's what I'm going to do. However, I think it will be an interesting exercise to show that the energy momentum tensor for the Proctor fields is given by that. Okay, I can give you a hint. Look into Jackson Books, 3rd edition, chapter 12. I guess that should be exercise 16 or something. Using his formula there for the energy momentum tensor is again reverse of what we obtained. I think by a kind of a sign difference. He's using the same kind of Lagrangian used in Landau and Lipschitz book, which is their classical theory of fields. You just have to substitute this Lagrangian into that expression. Just look into the chapter, it's somewhere there, just substitute this there, and then you obtain this. It's not too much of an exercise. I think it will be a good exercise to try your hands on that if you are learning this just for the first time. So, having said that, I proceed to do what I feel might be a little more, I don't think it will be too much of a challenge. But anyway, the point here is we proceed at this point in time to show that when we differentiate this Proctor energy momentum tensor with respect to x alpha, we are going to obtain something like this. Something more like the same, exactly the same as that of the Maxwell's Lagrangian. So we just want to show again that it's still not conserved, and again by almost the same kind of factor, and that's what we're going to do right now. Okay. In the same vein as we did for the Maxwell energy momentum tensor, we are going to do the same thing here. The alpha here of theta alpha beta, I'm going to have 1 over 4 pi. The alpha here of some g alpha gamma, f gamma lambda, f lambda beta. I'm going to have 1 over 4 again. The alpha g alpha beta, f lambda nu here, plus some 1 over 4. The alpha also, okay, no, I don't have any 1 over 4s following me anymore. I have 1 over 4 just for that second term. So this will be mu squared. For the sake of convenience, I'm not working with this here, so I'll just put comma alpha. I hope you know what that means. It's just the same as that. Minus again 1 over 2 mu squared. This time I would like to do this. G beta, A lambda here, A lambda, and that is what I get in this case. Yeah. Now looking at this expression, a moment please, I need to get a marker to. Okay, proceeding. Just like we did before, like I said, I'd like to use this metric tensor to raise that index on the partial differential. So this is 1 over 4 pi. I have here with me, in the end, this will be gamma, acting still on this, gamma lambda, f lambda beta. And then I have here with me plus 1 again all over 4. And this, okay, now I wouldn't have to do that. To avoid confusion, this will have to be raising this. It becomes the beta in this case. Okay, sorry, in case I didn't explain, this again was used to raise this alpha, and it becomes gamma. And just like we did before, again, it's acting on these two factors. And so I do that. I do the same thing here. I raise this alpha, and it becomes beta here. And this is acting on lambda nu, f again, lambda nu. The next thing I have again plus is mu squared here. A, alpha, A, beta, like I said, comma, alpha. Now looking at this last term, it will be minus 1 over 2 mu squared. If I raise the alpha here, it's going to be the beta, but then A lambda, A lambda. Okay. At this point in time, I can decide to do something. Again, the usual thing, of course, this will be 1 all over 4 pi. Looking at this expression, by Leibniz rule, this is lambda. I put a comma here. I have a gamma on top. I keep the second one constant plus I keep the first one constant. I differentiate the next one. This is lambda beta. The comma is down, but then the gamma is on top. This again is going to give me plus some 1 all over 4. Okay, I think I should just try to keep another bracket, something like that. This will give me f here, lambda nu, comma beta. Of course, I'm keeping the second one a constant this time. And then I have here with me lambda nu, but then f here, lambda nu, I'm going to have here with me comma beta. I think that's just fine. Yeah. Okay, now in the next term, I have this. I'm going to have plus here, mu squared of A alpha, A beta, comma alpha. Now on this last term, I would like to do something momentarily just for now. What is in the bracket here is really a scalar. I'm differentiating. This is beta. This is A lambda, A lambda. For the sake of convenience and ease of computation, as you can see, because every other term here, a lot of common indices, lambda is a dummy index. I would like to make it alpha. And that doesn't really affect anything on that term because it's a scalar. Making it alpha will make it easy for me to be able to combine these two terms. Okay, now looking at what we have so far, as you can see on this term, okay, before I make that, yeah, I think I can wipe this out and hope it wouldn't hurt as we proceed. Yeah. So the next thing I can do is to say that this is the alpha, here alpha beta. Looking at this expression, I have 1 over 4 pi. Again, with what we had before, if you look at this, you can see from the explanation we've made, okay, we have something else that looks like this. We have the Maxwell equation to be in this form, or if you like, you can lower both indices on top. And then again, you will have to raise this one. Then this is what you get. So you should take note of something here. The nu and nu here, these two are the same. But then if you look at this expression, I have gamma and lambda. And gamma here. If what I had here was lambda, gamma, comma, gamma, then it will simply be equal to 4 pi over c j sub lambda. But because it's now interchanged, what I'm going to have again is minus, but then 4 pi all over c, and this will become j sub lambda. Lambda again because the gammas are the ones contracted, and that is multiplied by f lambda beta. And then looking at this expression, all I have to do is just, of course, write that term the way it is. And this is f here, lambda beta, comma, gamma. That's for this one. What I have here in the bracket, this is going to be, again, like I've said, I'm going to try to avoid repeating myself. Now you can see, first of all, that lambda and nu in this case, and I have lambda and nu here, just in the same order on those field tensors. I can raise these two indices on top in that order, and with the metric tensors with which I raise them, I can again use to lower these two in that same order. And if I did that, then this term would be exactly the same as that. And just like we've done before, this then becomes 1 over 2 instead of 1 over 4. And what I'm going to have is f, but then lambda nu, f here, lambda nu, comma, beta. So these two terms have been combined to give me that. Now looking at this one here, I have already, for the sake of convenience, made some interchange, written this in this form. So I can have, so let me say mu squared a alpha, comma alpha, a beta, plus some mu squared. This time I'm keeping a alpha constant, but then I'm differentiating a beta by alpha. And the next thing here I'm going to have is minus 1 over 2 mu squared. So I'm going to try to do the same thing here to see how to make any combination or whatever that would be of help to me. I'm going to have a subscript alpha, comma, beta on top. I'm keeping the second factor constant, minus 1 over 2 mu squared, a sub alpha. This time I'm keeping that constant. But then I have the second one, a alpha, but then I have a comma and then a beta on top. And this is what I get, re-evaluating this term. So you can see for the first term, I keep this one a constant and differentiate this. Since the beta is on top, again the comma and then the beta is on top. And minus, of course, because they both have a common minus sign. But considering these two terms, it should be plus. Again, I keep the first one constant and then differentiate the second one with respect to x beta with the index raised in that form. Now, looking at these two terms here, I have here gamma and a lambda. And if you look up here, you can see lambda and a beta. In order to facilitate my combining these two terms here, I'm going to try to change this to be the same as that, especially this. So whatever transformation that I can make to make this field tensor exactly the same as that is what I'm going to do. First of all, you can see that I can decide, for instance, to change this lambda everywhere to gamma. Yeah, I can decide to do that because it's just a dummy index. I can change that to gamma, and this is what I'll have. Then the nu here, I can decide again to change to lambda. I can do that again because nu here on this term is a dummy index. So this becomes lambda and this becomes lambda. And now you can see that these two are the same. Okay, now in order to avoid wasting so much time, I would suggest please just check the previous lecture and you will realize that we were able to combine just something like this, two of this. Instead of doing this all over again, we spent quite some time there to show that this 2 gives us 0. When you combine and in the end you are going to get the totally contravariant form of this expression, the homogeneous Maxwell equation. Which of course we said is still true for the Proctor-Lagrangian. And so because of that, that part of the expression is 0. So having said that, I'll simply just move on with the rest of the terms. Now for the rest of the terms, you can see we can try to make some combinations here. First of all, again, we have believed and stated that this is all in the Lorentz gauge. So in the Lorentz gauge, it means also that this term is 0 because this factor is 0, so I wouldn't have to bother myself or worry so much about this one. Now, looking at these last two terms, now there is something again I'm going to do, which will be interesting again because, like I've said before, so trying so much here to see if this works out. Okay, well, I have beta on top. I wouldn't want to mess with that, but I have alpha in this state. This alpha going like this and alpha going like this. So I like to make this term look exactly like this one. And the only reason why I'm going to do, of course, is because I can. But then look at this quite critically. If I raise alpha, so let me just okay. I think it would be good we just write the whole thing without the things that I've reduced to 0. This will be minus 4 pi all over c j sub lambda. This is lambda beta. This part is 0. We don't have to bother ourselves about that. This is 0, and we are left with some plus mu squared a alpha. Okay, I think I'd like to do something on this one too. Yeah. Just like the trick I tried to explain initially, this index is just on one object, and this index is just on one object. If you remember, it is on the differential d sub alpha. So this factor might as well be written as this. And so I can decide to raise alpha and lower it. In other words, this term might be written the same thing as that. This becomes a sub alpha down here, but then a beta with the comma and alpha goes up, like we've done before. With the metric tensor with which I lower this index, I can use to raise this one. And then again, it's the same thing I want to do here. I want to bring all this in the same form. So I'm going to again raise this one and lower this one. So instead of fusing around with the metric tensor, if I use a metric tensor to raise this index, I might as well at the same time use it to lower this one. And that's what I would like to do, so that this will become minus half mu squared a alpha comma beta a alpha there. And then minus, of course, what we have there on the last term. Oh no, I thought I could compress that in here, but let's just make some space. So this gives me here, on the last term, I'm not making any transformation on that last term. I'm leaving it just the way it is, comma beta. But looking at these last two terms, they are just the same. Okay, sorry, I made a transformation on this term, which wasn't complete. So if you remember, when I raise this alpha, I am supposed to at the same time lower that one. Yes, that's the idea. And it's the same thing we did here. When we lower this, we raise that one. And we said, of course, we've said that severally as to why we can do that. Now, if I combine this and this, so of course, this will give me 1 over 4 pi minus 4 pi all over c j lambda f lambda beta. And this will be plus mu squared a sub alpha. A here, this will be beta comma alpha. Now, if I combine these two, which are the same, I will simply be doing, and we're dispensing the half there. This will become just minus mu squared a sub alpha, a but then alpha, comma beta. Since the two are the same. Of course, what I'm going to do next is have to combine these last two terms. These last two terms. And take note that these are common. So I'm going to have something like some mu squared. I'm going to have something like some mu squared a sub alpha, and then a beta comma alpha minus a alpha comma beta. And of course, you can recognize this already. This is the same thing as f, I believe, alpha beta. Yeah. Remember, because if this actually means the alpha a beta, right? That's what it actually means. So this is what I get for that. So in other words, my expression in the end looks like 1 over 4 pi minus 4 pi all over c j sub lambda f lambda beta. But then in the end, I'm going to have, sorry for the confusion, this is going to be simply plus mu squared a sub alpha. Yes, I believe that's what it should be. That is a sub alpha, but then I have here with me f alpha beta. That's just what that is. We just show that this could be written as that times that. So we factored it out. Okay, making space for us from the top here to see how further we can go with that evaluation. Okay. I have here with me lambda and lambda, which I would like to change. Yeah. Okay, well, maybe first of all, take note of this. The alpha, theta, alpha, beta is the same thing as 1 over 4 pi. I can write this as just 4 pi all over c without the minus sign. But then again, it will become f on top here. This becomes beta lambda. And then remember, this will be, of course, plus mu squared a alpha, f alpha, beta. This is what I get. And then again, I can change the lambda to alpha, which I can do because lambda is just a dummy index. So this is alpha, alpha. Oh, well, I don't know if this is of any use or if it wouldn't be at all, but I have already made an interchange that changed 1 to minus. I guess. So if that is the case, what we've got here is the fact that I have something here that is common, which I can pull out. And of course, it looks like the only way I can pull anything out after all is to have to make some interchange here. So if that is the case, so I think I'll prefer to make that interchange on this one. So this will be 1 over 4 pi, and this will be 4 pi all over c. This is j here. This will be subscript alpha f beta alpha minus mu squared a alpha, but then f here beta alpha. So the interchange between alpha and beta is what gives us this minus sign. So I can pull out the f beta alpha. So let me do that here. This will become here f beta alpha. Maybe I can just put that at the far left. I think it wouldn't spoil anything. This will be 4 pi all over c j sub alpha minus mu squared a sub alpha, and then what I'm going to have at the end is f beta alpha all over 4 pi. I guess that is it. Yeah, that is what it should be. Okay. I just might as well be running the cycles, but it's quite easy for me here to see that. Okay, now very sorry to say that really made. I think I messed up a few moments ago. Please, let me just take this one step at a time, and I will explain. We have worked with. I've been working with a very wrong result all this while. For instance, from the beginning, when I was finding the derivative of this, if you remember, you just have to please play this video back a little bit. The very first term on that expression was this. And the next thing I did on that term was to raise this alpha and then obtain something like that. And the next step was, of course, to differentiate these two, or this object here by Leibniz rule. That's differentiating the first one, which is that, keeping this a constant, plus I keep this a constant, I differentiate that. Now everything has been correct up until this point in what we have been doing so far. Everything has been correct until the moment when I said that this, for instance, was equal to minus 4 pi over cj sub rho. And quite frankly, and that's the only thing that was wrong in the few moments ago, because this is only true, or this expression, or this will be equal to that, only for the Maxwell-Lagrangian, or the Maxwell equation. This is obtained from the Maxwell equation. But if you look at the, since we're working with the Proctor-Lagrangian, or talking about Proctor fields, the true equation of motion is actually that. So all along, or all this while, I remember this term was added to some other one that gave us 0, and every other manipulations we have been doing so far has been right, except for the thing that we substituted here. And I substituted here to be minus some 4 pi over c j something times that, which is all wrong. I shouldn't have done that. In other words, this shouldn't have been there in the first place. I just realized that now. Well, thank goodness I did that right on time. But I just saw that that was what caused the problems that were encountered here. So everything has been correct, like I said, except for the fact that in the process, at some point I substituted this to be minus 4 pi over c times that. So just look at the whole calculation once again, but this time around, just imagining that we didn't substitute anything for this. And I'm going to work with that. And if I didn't substitute anything for this, everything else would just give us exactly what we obtained. Because so far, if you remember, like I said, we combined this with another one that gave us 0, and we manipulated the rest of the terms, and this is what we would get. Okay, having said that, if we got to this point, the next thing we are going to do actually is to see that this, for instance, I can change the lambdas to alpha, which I can do again because lambda is just a dummy index. And so this gives me gamma here, and that is alpha comma gamma, and this is going to be alpha beta plus mu squared a sub alpha f alpha beta. Now this is the same thing as 1 over 4 pi, This is the same thing as, again, in the bracket, F gamma alpha comma gamma plus mu squared A sub alpha, then F alpha beta. Now, it was important to have to take note of this mistake, really. I'm very sorry for that, but then again, it's just to make you see that this expression here, of course, I could have written this as the gamma F gamma alpha plus mu squared A alpha. But then if you look at this expression here, the only thing, of course, is that the beta here in this case have been replaced by gammas. And so when I have this, which is the dummy index, of course, so you can just write gamma if you like, but then we have alpha here is the important thing, plus mu squared A sub alpha. So this whole expression here, this expression here is just the same thing as some 4 pi all over C J sub alpha. So this is what is actually equal to 4 pi over C J sub alpha for the Proctor-Lagrangian or from the Proctor equation of motion. The first mistake I made was to assume that that will give me this, but that will be according to the Maxwell equation or Maxwell-Lagrangian, and that will be completely wrong. Sorry, I got carried away, I forgot all about that, but having said that, it therefore means that what we have written so far is the same thing as this is 1 over 4 pi, and then what is in the bracket is 4 pi all over C times J sub alpha, then this here becomes F alpha beta. Of course, these two go. And then in the end, turns out, in this case, turns out in this case, that what we get for the Proctor-Lagrangian is that this is equal to 1 all over C J sub alpha F alpha beta. Of course, if you decide to interchange these two, you get the same thing as we had for the Maxwell equation. This is again going to be beta alpha. So just as it was for the Maxwell equation or the Maxwell-Lagrangian, that's in talking about the energy momentum tensor for the Maxwell equation, we obtain that the conservation law in this case, that this is not conserved, and what you get on the right hand side instead of 0 is this. And we have, of course, shown in this case that this is the same thing this time around for the Proctor-Lagrangian. So sorry for the mess up. I hope all that has been cleared up. It might take a little work of just rewinding this video and you get everything right as you should. Let's hope to see you again in our next presentation.